Welcome to the new era of video creation with Baozi. This is our new series on teaching deep learning. Today, we will discuss the transformer in neural networks. Here are the contents. The transformer architecture has revolutionized deep learning, especially in natural language processing, NLP. Unlike traditional recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, transformers don't rely on sequential processing. Instead, they use a self-attention mechanism that allows the model to process all inputs simultaneously, leading to significant improvements in parallelization and performance. Initially proposed in the 2017 paper Attention is All You Need, transformers have become the foundation of many state-of-the-art models such as BERT, GPT, and T5. Their ability to efficiently capture relationships between distant elements in a sequence, without relying on sequential data processing, has made them the architecture of choice for a wide range of tasks, including machine translation, text generation, and even image analysis. In this lecture, we will explore the key components of the transformer architecture, how it works, and why it's become the go-to model in modern AI. The self-attention mechanism is the core innovation behind the transformer architecture. In simple terms, self-attention allows the model to evaluate the relationship between different words, or tokens, in a sequence, regardless of their position. This contrasts with RNNs or LSTMs, which process inputs sequentially and struggle to capture long-range dependencies effectively. Self-attention operates by creating three vectors for each word: query, Q, key, K, and value, V. The query vector represents the word's current context, the key represents the words to which it will compare itself, and the value vector holds the information to be passed forward. The attention score between two words is calculated by performing a dot product of the query vector of one word and the key vector of another word, followed by a softmax operation to produce a probability distribution. This mechanism enables the model to focus on different parts of the input sequence when making predictions, significantly improving its ability to handle long-range dependencies. The scaled dot product attention is an essential component of the self-attention mechanism. In traditional dot product attention, the attention score is simply the dot product between the query, Q, and key, K vectors. However, the values of the dot product can grow too large as the dimensions of the vectors increase, leading to large gradients and unstable training. To mitigate this issue, scaling is applied by dividing the dot product by the square root of the dimension of the key vectors, denoted as dkas kruti dkas. The formula for the attention score becomes attention QKV, softmax QKTDK, yeah, text, attention QKV, yan text, softmax, left, einfrak, QKT, uskroti, DK, right, vi. This scaling factor ensures that the gradients are more stable and that the model can train more effectively. After the scaling, the result is passed through a softmax function to obtain a probability distribution, which is then used to weight the value V vectors. This self-attention mechanism is crucial for enabling the transformer to capture the relationships between words at various distances in the input sequence. Multi-head attention is a key feature of transformers that allows the model to learn multiple aspects of the relationships between words in parallel. Instead of using a single attention mechanism, multi-head attention splits the query, Q, key K, and value, V, matrices into multiple smaller heads, each learning a different attention function. Each head performs the attention operation independently, capturing different parts of the sequence's information. The results from all heads are then concatenated and passed through a linear layer to form the final output. This technique allows the model to attend to different semantic and syntactic aspects of the input sequence at the same time, improving its capacity to understand complex relationships between words. For example, one attention head might focus on syntactic structure, while another might capture long-term dependencies between words. The ability to learn multiple attention functions in parallel is one of the reasons why transformers perform so well on tasks like machine translation and text generation. One of the challenges of the transformer model is that, unlike RNNs or LSTMs, it does not have an inherent sense of the order of words in a sequence. Since transformers process all input tokens simultaneously, they do not have the ability to inherently capture the sequence's structure. To address this, positional encodings are added to the input embeddings to inject information about the position of each word in the sequence. The most commonly used positional encoding method is sinusoidal encoding, which uses sine and cosine functions of different frequencies. The formula for the positional encoding is PE, POS, 2I, sin, POS, 1000, 2I, D, PE, tia, POS, 2I. Charge he sins left, jar frac, POS, 1000, 2I, D, aj right, PE, POS, 2I, by 1, COs, POS, 1000, 2I, D, PE, POS, 2I, by 1. Raj cost left, frac, POS, 1000, 2I, D, as right. Where POS is the position of the word, di is the dimension of the encoding, and dd is the total number of dimensions. By adding this positional encoding to the input embeddings, the transformer can distinguish between the order of words, enabling it to handle sequential tasks like text translation or text summarization effectively. The transformer architecture follows a encoder-decoder structure, which is particularly useful for tasks like machine translation, where an input sequence, e.g., a sentence in one language, needs to be translated into an output sequence, e.g., the corresponding sentence in another language. The encoder processes the input sequence by passing it through multiple layers of self-attention and feed-forward networks, generating a set of representations that capture the contextual information of the input. The decoder uses these representations, along with its own attention mechanism, known as cross-attention, to generate the output sequence. Each layer of the decoder has two types of attention, one that attends to the encoder's output, cross-attention, and one that attends to the previous token in the output sequence, self-attention. This structure allows the model to effectively map sequences from one domain to another, making it ideal for tasks like machine translation, text summarization, and image captioning. In addition to the self-attention layers, each layer of the encoder and decoder also contains a position-wise feed-forward network. This network consists of two fully connected layers with a non-linear activation function, such as ReLU or GeLU in between. The feed-forward network is applied independently to each position, word, in the sequence, allowing the model to learn complex transformations at each position. This design is particularly efficient because it applies the same transformation to each token without any interaction between different tokens. Each encoder and decoder layer also includes residual connections and layer normalization to stabilize the learning process and enable deeper models. The use of these components helps to reduce issues like vanishing gradients and accelerates convergence during training. The transformer model consists of two main components, the encoder and the decoder, each made up of several layers of self-attention and feed-forward networks. The encoder takes in the input sequence, applies self-attention to capture dependencies, and passes the result through a position-wise feed-forward network. This process is repeated for each layer of the encoder. Similarly, the decoder generates the output sequence by using both self-attention and cross-attention mechanisms, attending to the encoder's output and the previous tokens of the generated sequence. Each layer in the encoder and decoder also includes residual connections, which help maintain the flow of information across layers, and layer normalization, which normalizes the output at each layer to stabilize training. The stacked structure of these layers allows the transformer to model complex dependencies in the input and output sequences, enabling state-of-the-art performance across a variety of tasks. The transformer architecture offers several advantages over traditional RNNs and LSTMs. One of the key benefits is parallelization. Unlike RNNs, which process inputs sequentially, transformers process all tokens in a sequence simultaneously, making them highly efficient for training on modern hardware like GPUs. This parallelization significantly reduces training time, especially for large datasets. Additionally, the self-attention mechanism allows transformers to capture long-range dependencies more effectively than RNNs or LSTMs, which struggle with long-term context. Transformers have set new benchmarks in a variety of NLP tasks, including machine translation, text generation, and question answering. Furthermore, their ability to scale to large datasets and models as seen in models like GPT-3 and BERT, has made them the go-to architecture for many cutting-edge applications in AI. Pre-trained transformer models such as BERT, GPT, T5, and Roberta have become a foundational part of modern NLP. These models are first pre-trained on massive corpora of text data, learning general language representations that can be applied across a wide range of tasks. For example, BERT is trained using the masked language model task, while GPT uses autoregressive language modeling. After pre-training, these models can be fine-tuned on specific downstream tasks, such as sentiment analysis, named entity recognition, or question answering. This approach, known as transfer learning, allows models to leverage pre-learned knowledge and achieve high performance, even with relatively small amounts of task-specific data. This has made transformers incredibly versatile and effective across a wide array of AI applications. Transformers have found applications in various domains, with NLP being the primary area of success. In NLP, they are used for tasks such as machine translation, text summarization, question answering, and text generation. However, their use is not limited to language. In computer vision, transformer models like VIT, Vision Transformer, have been shown to perform well in tasks such as image classification, object detection, and image captioning. Transformers have also been applied in speech recognition and speech synthesis, enabling systems like voice assistants to perform with remarkable accuracy. More recently, transformer models are being explored for time series forecasting in domains like finance, healthcare, and climate modeling, demonstrating their versatility across different types of data. Despite their numerous advantages, transformers also face several challenges. One major drawback is the high computational cost associated with training large transformer models. Due to the self-attention mechanism, the time complexity of processing a sequence grows quadratically with respect to the sequence length, making it computationally expensive for long sequences. Additionally, transformers lack the inherent inductive bias for sequence data that RNNs and LSTMs have, which means they require more data and training to achieve good performance. Transformers can also face memory bottlenecks when dealing with long sequences, especially when the sequence length exceeds a certain limit. Finally, large labeled datasets are often required for pre-training, making the architecture less accessible for smaller tasks or domains with limited labeled data. Recent advances in transformer architectures have focused on improving their efficiency and extending their capabilities. Efficient transformers, such as linformer and reformer, have been developed to reduce the computational complexity of self-attention, allowing the model to process longer sequences more efficiently. Additionally, sparse attention mechanisms have been introduced to further reduce the computational burden. In the multimodal space, transformers are being used to handle text and image inputs together, as seen in models like Visual BERT and CLIP. Longformer and other models have been developed to specifically handle long-range dependencies in very long sequences, making transformers more practical for tasks that involve lengthy inputs, such as document classification or legal document analysis. The future of transformers looks promising as research continues to explore more efficient and scalable models. One of the main directions is improving the computational efficiency of self-attention through techniques like sparse attention and low-rank approximations. Moreover, we can expect cross-domain applications of transformers, where models will be trained to process multiple data modalities simultaneously, such as text, image, and audio. Integrating transformers with reinforcement learning could open up new possibilities in robotics and autonomous systems. The application of transformers in healthcare, biomedicine, and scientific research is also an exciting area of growth, with the potential to improve drug discovery, genomics, and clinical diagnostics through better modeling of complex high-dimensional data. In conclusion, the transformer architecture has fundamentally changed the landscape of deep learning, especially in NLP and other sequential tasks. Its core innovations, such as self-attention, multi-head attention, and positional encoding, allow it to efficiently capture complex relationships in data, making it highly effective across a wide range of tasks. Despite its challenges, Ongoing research is focused on improving its efficiency and extending its capabilities to new domains and tasks. The transformer's versatility, scalability, and ability to model long-range dependencies have set a new standard in AI, and its applications continue to expand in areas like multimodal learning, healthcare, and science. Thank you for your attention, and I'd be happy to answer any questions you may have.